of systems are really kind of intriguing. I'll talk about the questions that are still open, and then let's go to the. So this is the thing. Like you have insulating state, which is correlated insulating state, and next to that there's a superconductor. This was 2018, and we are 8 years after that. Oh, this is here. So this is something that, as I said, the word chiral Yuval doesn't like. Hero hates it, I guess. So everybody doesn't like it. So forget about this. This is a Nature paper with the title. So forgive me. So the thing is that this is a pentalayer. This is basically have seen in a few layer graphene. So it's not like a 5-layer graphene. You see the superconductivity. No, it's basically you are seeing it in 3-layer, 4-layer, 5-layer, 6-layer. And what you see basically is that in this place, if you guys can see my mouse, so this is the place. This is quarter metal. So all the degeneracies have been lifted. I guess you guys know that for graphene we have 4 kinds of spin and pseudospin. So this is quarter metal here. Of course, the quantum oscillations inside this superconductor is very difficult to see. I didn't put here the new one. This is, if any of you are interested, there are a couple of papers, one from Weizmann, one from UCSB, actually 2 from UCSB, and also Stanford, that is with the squid, etc., that people showed here that there are some domains here. Okay, so in short, I can tell you, if I want to be correct, it's a magnetic superconductor. So there is some orbital magnetism here. So it's already pretty interesting superconductivity with all sorts of stuff. And but my enthusiasm about this system is that if it is offering us so many kinds, maybe even chiral will pop up one day. So I'm optimistic about it. And then comes the next one, which is not graphene, by the way. This is MOT2 twisted. The reason I'm interested in this one, it's because of the fact that if you see that there are FCI states here, okay? And the superconductivity, I know that it's a very small blob of it. I am not sure yet why this paper is more than a year sticking to archive, but this is from Tinxing Li of Shanghai, that there is superconductivity in MOT2 just next to the FCI. Like as I said, that our motivation for doing this, this Wigner crystal is exactly coming from something close to this, that FCI and superconductivity can be next to each other, which is, I'm sure for many of you that are talking about Majorana interface of, quantum Hall with superconductor, and we always talked about, how to have a seamless, junction. This is basically gate-defined stuff. So all you see, this axis is just electric field. So you have 2 gates, and you are controlling the entire phase diagram. You don't even need magnetic field to see all these fractions that they see. And you see also next to it superconductivity. If you ask me, Mitali, as an experimentalist, the device is going to be easy to make? No, but then you have a bunch of PhD students. So just start working on it.
So which part of superconductivity?
Sorry?
You said that there is a time superconductor. That's blue, but there is a
This is
twisted MOT2.
Yeah. But I mean, there's a large blue region.
This one is basically RxX. So it's like you have mu c equals to 1, also have RxX 0. So I give a line cut here.
I see.
So this is where you can see that for other states.
You have to know.
Yeah. I'm sorry, I could not put too much, and I didn't know the audience. I didn't want to overload people. My interest. So the last one is this one. This is also recently got accepted in Nature. This is all about having all sorts of superconductors. But what is interesting here, that it actually breaks, like in a way, I just said that doesn't really.
What is the material? Is it bi-layer?
No, this is 5-layer, 5-layer, 4-layer. This is 5-layer and 4-layer. Both of them are there. This is R4, the 4-layer one, and the one next to it is R5. So what I want to say is that perpendicular field is 0, but parallel field is 8.5 Tesla. The reason for the red line is that it is inverting the textbook Pauli limit.
That seems to be universal, right? In many of these materials.
Yeah, so many, since the Young showed for the first time, showed that you can actually have these phases in 8 Tesla or something.
Yes, but the point what I want to
What?
yes.
Yeah, the period of
Superconductivity.
Okay, so all I want to say is that this is in one platform whereby tuning your gates and tuning your magnetic field, you are bumping on different states. I'm sure in bilayer graphene, in parallel field, with the TMD, etc., people have seen, but this is like something
But
you are getting.
what did you just say something about the Pauli limit? You said you are inverting the Pauli limit?
Yeah, it's in the textbook, you know, it's a parallel one that you calculate for this because it's a very thin sample.
Right.
And then you will find out that indeed it's basically breaking. It broke also before. It's not the first thing. What I want to say is that this rhombohedral graphene or few layer carbon, where the more is only needed when you need FCI. So that part I skipped here because I know that here the audience is more into superconductivity. If you just put a more on one side, which I know Tero can explain to you well, that why you need more to see FCI or this kind of states here.
Fractional churn insulator, right? So not everybody was.
Yeah, fractional churn insulator, which is also in the MOT to 1Cs. So
what is the system again?
It's 5-layer or 4-layer or 6-layer.
Rhombohedral ABC graphene.
No, it's the
ABC graphene. It's rhombohedral graphene.
It's just rhombohedral
So
graphene.
what would be the main question that you would want us to talk about?
So.
What mediums it have?
Yes. Okay, so if you agree with somebody, let us know.
Many think it's come from electron interaction, right? That's what made
If a blanket
positive interaction.
It's not electron phonon. It's electron.
Many believe. I didn't say.
This is the point.
How do we know it's not electron form?
The question is, what would be the experiment to distinguish between?
I think there was not a tunnel experiment where they said that they didn't see a change by going from carbon 13 to carbon 12. I don't remember exactly. I think it's in the isotope.
Carbon 13.
But every sample is slightly different. So if you take another sample with different carbon, it's also going to be different. So what does it tell?
So about that, I can tell you that I'm very happy with rhombohedral graphene also because this is gallium arsenide 2.0. Like I can give you the three devices from my lab that behaves in the same way, except for maybe the resistance is 400 or 500 ohm when you are measuring normal state, like or 450 ohm. So maybe when I said nobody agrees, I wanted to mean that people among each other in this room, maybe everybody agrees. I leave the room, somebody is telling me.
Discuss what is the exact mechanism.
Yeah, so other parameters also one has to make some corner junction, just following, yes.
Yeah,
But
I had a question
it's
about.
not even clear that the mechanism for the rhombohedral for the magic angle is the same.
No,
It's not the same system.
no.
Rhombohedral can well be electron form.
But is it clear how to measure the other parameter?
So that
What is the key experiment?
So there's the V shape that Pablo's group saw in the tri-layer tunneling they did published a few months
also in
ago.
Caltech, this all right.
Yeah.
So what is V shape? That means that you
It's
have
so a gap shaped like a V, right?
It's not a,
okay. So
Yeah, so you say,
True,
okay, many
true.
things can give you a V shape.
exactly true.
Yeah.
That's why it's not sufficient, I'd say. So I can say something that I learned from Preden, that they are doing some, maybe all this more, that there is, they are trying to calculate with the noise, like if it's D wave and if it's P wave, and in certain angle, like you can have this angle dependence in the noise that will be reflected. The only thing is that when you're measuring noise in a particular hall bar,
angle of what?
oh, this lobes that they D and P that has this plus minus, this kind
What
of.
are you changing?
Yeah.
What are you changing? The current direction or?
So this is the thing, like if you have in a sample in one direction you measure and then maybe you send the sample.
It's just a measure of noise in transport.
Yeah, something like this. But then they're calculating
Current. Current to the sample edge.
no, it's where is it? Superconductor.
So what?
So it's a resistor. It's a resistor.
Resistor.
Yeah, it's a resistor where you are sending. And now, if you have this kind of complicated geometry, yes.
So, I mean, I'm not at all in this field, so maybe this is very naive, but it seems like some of the systems have more than one superconducting dome, right? Like what you
Many.
And here's a thing: has anybody ever? So if you have some strange symmetries, like not S basically, if you have a S-wave superconductor with to create the Josephson junction with the system, if the symmetries are incompatible, this should kill the Josephson current. Am I mistaken?
Right.
Yeah.
So
Supercurrent from S wave to P wave is supposed to be zero.
exactly. So if
Unless your scattering in between is such complicated.
But there's a methodological problem with this proposal is that if the mechanism is strongly related to electron-electron interaction, by placing a superconductor nearby, you're screening these interactions. It's not so trivial that what you measure is actually the system. The system is actually identical to the one which is the standalone system.
The other component will also be screened because there is always an interaction.
Yeah, so so that's kind of a challenge if you want to do this particular. And still, then again, you have people do measure tunneling either from STM, which still it's a small tip but still screens, or from a neighboring tri-layer, which they probably have some argument why it screens less, but I'm not sure what the argument is.
The STM here is problem because you need to have both gates in order to go to any of the superconductor because they are at finite D field.
Yes.
So it's not simple.
But you can change the thickness of the HPN.
This you can do, but the STM cannot sense that. It needs an open surface, right? The only thing is the squeak. That's why I was telling you that these papers of domains and stuff, it's a squeak scan. Yes, he has a question.
Can you connect different layers and measure transconductance between different layers?
Actually, this is a good thing because it turns out.
Drag experiment or a trap?
Just transport, they are all connected. Suppose they connect
Top one and the bottom.
top one, both and
Yes.
the second one and the third one. That can teach you a lot without changing.
You're saying in a rhombohedral or a magic angle?
Yes.
No magic
Yes.
angle.
Yes to everything.
Yes to everything.
No, but when you say rhombohedral,
between the layers.
connecting individual layers within a rhombohedral or two different rhombohedrals?
Individual layers within a room. If you don't cut all of them together, it's possible.
But still, you get the part of the same band, so you can't do there. It's a resistive network, so you can't really measure individually each one of these bands.
The states are localized in the surface.
Exactly.
So therefore you want maybe the top and the bottom.
So if you have the top and bottom, you can actually have a vertical Josephson junction. That's a very nice thing to make.
That's also, and also you can imagine scattering from non-interacting area when there is no 4 layers to an area with 4 layers to be an NS junction.
So this kind of stuff is a bit tricky because, as I said, that this material kind of relaxes to Barnell. Though if you look into papers, they will say that Barnell is less favorable energetically than rhombohedral. But the truth is that most of the time our problem is that it gets relaxed. And Andrea has, again, those of you who are interested, Andrea has a paper now on archive to maximize the area and, have the process to make the stack that is way less stressful to say. But what Yuval is saying, in theory, possible. In practical, maybe in 100 years. Or somebody from China.
I have a question for all these rhombohedral experts around here. Suppose I can look at supercurrent running through the surfaces and carry out some kind of a squid measurement that I can actually, with a parallel field, actually introduce phase between the top and the bottom layer. Will I learn anything useful by making this experiment? if suppose it could map using like similar ways. It was a talk, it was Chuan gave a talk yesterday, which is like the standard way you measure current distribution in a for example, in graphene or any planar material. You do the Fourier analysis of the
I'm trying
front
to
half.
think what.
So suppose you do this, but you apply parallel field, and you have supposed to have the superconductor running in parallel at the top and bottom surface. How do you measure? What? You measure the IC versus field
Of the whole device.
Yeah.
With parallel field.
Yes. Okay. Is it useful in any way? Is that
My understanding that because you need to apply the D field and
I need to apply the field just to get.
The different surfaces will have a different order parameter, and it could be that only one of the surfaces.
So you say I need to apply the filter just to stabilize the superconductor.
Yeah.
Yeah.
So which means that actually you break the symmetry between top and bottom.
Anyway, I need to apply this.
Yeah, but you need a displacement.
You need. It's all
So
finite.
that will not be, it will be on one of them.
Yeah, exactly.
So, sister, we're still on the question of how to measure your.
But it might be still interesting because I guess none of these experiments really prove it's only on one layer, or do they?
No, people did make experiments.
I mean, you
five layers.
measure resistance and
Yeah.
or maybe it's so that one of the layers is magnetic and the other layers.
No, but suppose one somehow contacts the top and the bottom layer, like measures the potential individually on the top and the bottom. Will something that be useful? Because again, people measure transport globally on the whole
Yeah.
device. This is what you do, right?
Yeah.
So you have contacts like which are these side contact, graphene side
Yeah.
contact, like chromium gold side contacts, something at the edge. You make like this whole bar and you drive current. So then the question is whether you can somehow throw voltage drop along the point.
So the idea that I had, I think you guys, I don't know that in Colombia they have this material. There's something. It's metallic. It's van der Waals. It's metallic. The idea is you take a bottom layer of that material, and you take your rhomboidal vacuum. You take another layer of that material, and you have to have. But then this is the metal, so it screens the entire rhomboidal thing. How do you gauge it? Right, you need to gauge. So that's the point. The point is that means that you have to contact the top and bottom layer from the side, and in between you have to gauge from the top and bottom. So that is the kind of stack that I see.
Yes.
That's the reason I mentioned, because only 10 days a hospital can be built in China. They can do it, nobody else. You don't know, in Corona, they built the entire hospital for 1,000 people in 10 days. So that's the record thing I know. That's a record thing. I tell this to my students, they will just run away. It's not gonna happen. Or I have to do it myself. But that's the idea that I thought. This idea came because of this MOT2 twister. If you see, they use TAS2 for their contact to the MOT2. Okay. In this paper, if you see, that's the. These guys are actually doing the harder work. This, you see, TAS2, yes. This is the way that they contact the MOT2. Because the way I do my tungsten diselenide contact is just platinum, and I put the flake on top of it. But this is way better. That's why he sees what he sees.
Why? Because that's a metal that that appeared. That's titanium or tantalum.
It's tantalum.
So that's a superconductor with a very, very small gap.
For that material, this is okay.
Yeah.
But I'll look up for the material that Corey is working with. It's a metal that Xavier Roy made. It's a van der Waals metal.
No, but the van der Waals metal is used.
But that's the thing. That's the metal. Like instead of the gold contact, you can make that contact on graphene from either side, and you just make, so you have top layer and bottom layer connected to two different materials, this van der Waals metal, and you have gates running all over. And then you have D and you have contacts, and there is a global gate that can dope if needed. That's it. That's all I can think of.
So you're having some trouble visualizing this. So with respect to this thing, what would you change?
Oh, so here you see, what they're doing is that this is a
We're
very,
allowed to use the blackboard.
yeah.
You can actually switch it off. If you want
Oh,
to
you
draw,
can
draw
just write
devices,
Yeah, yeah.
you are welcome to draw the switch.
With pleasure.
Yeah.
If you can make it, I will be more than happy. Anybody can make it.
You have to switch off the.
Sorry,
the,
no, no.
Yeah,
You can switch off the screen.
You can
So
switch off the
just to
screen.
get light here. I think there's a separate light, right?
Nobody sees this.
Same like my whatever.
Okay.
That's it.
So yes, whoever has been, I will find out the material in my phone. Now it's polite to look at the phone, so I'll pick up the words. So the thing is that you have this graphene layer that whatever you have, this is your rhombohedral. The idea is that you take this material that Curie has, a few layers, which is just like gold, the density is like that. And then you take another layer here. And in between, you have to have, you know, of course, graphite cannot touch it or stuff like that. So you have to figure out by putting a HBN here. So this is my HBN. And here also I have to have an HBN. And then you have your graphite, which, if you ask me, should be at least 3 nanometer if you are still working in this lab. And then there is a graphite here. So if you have that, then it should be the vertical Josephson junction. This is this vertical.
So basically, the idea here is to individually contact the top and the bottom surfaces of individual superconductors.
Because if you etch, you know, now you can say, Vitali, what do you think? This is going to fall down. And
No, I see the point of.
oh, it's like, namely, your graphene has to be very big and this has to be small. Your student will explain you how to do the stack. Trust me, it's not easy.
What is this super material?
Let me just give me 2 seconds now.
Is it Vanderbilt or the?
Yeah, it's Vanderbilts.
Okay.
It's Vanderbilt metal. What works with it? What's the name? They have to go to the chat.
So then, just while you're doing that, so I'm just gonna zoom out and say so that basically we're asking about all the parameters.
This is a Josephson junction, right?
So in all the parameter, one asks whether there's any use to put tunneling, and that was already done by MIT.
No, here the tunneling is not done. Here the tunneling is not done, right? Because whenever you have the top and the bottom gate, you cannot just tunnel.
Yes,
just
okay.
like
But you, so what you're saying is in rhombohedral graphene,
yes.
it's a top to bottom. But what do we learn from this top to bottom? It's the assumption there's actually 2 individual superconductors, which each one with its own ground state that you can.
I mean, you know, this is a fancy device you can make, and you can think about if this bulk is bulk and the surface states are.
Are you sure that you have superconductivity in both the top and bottom? Displacement.
For 1D, we can't.
Input displacement field, you can depopulate the top layer.
Maybe that's what you are measuring. Maybe that's what you want to measure.
Yes, it did happen.
But of course, the question
Well,
is, how would you know it's experiment? Because,
Well,
first of all, you have normal contacts to the superconductor. So you kind of make a probe measurement here.
So how do you know you're not somehow selectively gating laterally? Like maybe you're only gating the middle parts and not the
So
sides.
this is what I said. This is somebody, your student will make the device. Just give the idea.
No, that's people.
But even if you make it,
Yes,
you could be selectively doping.
of course, and then you have a global gate, right?
No, but there are local gates. People been in these devices. Okay, like there's something that in this conference we didn't really talk a lot about this kind of device. In the community of people who build these devices, there's a lot of work on like very narrow local gates. You could switch them locally from superconductor to insulator, and people build Josephson devices where you have the superconductor to insulator to superconductor, etc., etc. So we would have been doing that.
Yeah, what I'm saying is very silly, and maybe it's wrong, but I mean, this thing is metallic, right? So it will screen this part of the, it will screen this part. So maybe what you may measure something, but it may not be a top to bottom thing. You may be getting some inhomogeneity across the.
Yeah, because if you cannot have this all the way, because then you will not have it as the gate.
Yes.
Yeah, so that's not possible.
What are you were saying something about these corner directional.
Yeah,
So
so-
maybe you could develop this, because again, this is something that
Yeah.
the people with gray hair know what it is.
Exactly.
The people without hair don't know what it is. Maybe you can kind of
Yeah, so this is-
educate the crowd here.
yeah, so I don't remember the reference on top of my head, but on the corner you can have the JJ can be on the corner, and they did it for the high DC superconductor.
That's a great, great boundary junction.
Grain boundary junction. Yeah.
Yes.
Yeah, that's the other by junction.
Yeah, it's a new wave, so you put.
Yeah.
Yeah, first author Kid Winjira, right? François. Yes.
That's the one.
But she left academia.
See, you see, this is what happens. You put too much pressure, people are leaking out.
It was a great paper, though.
To have happy smile all the time in the face, you have to.
So again, but so the idea here is if you have an order parameter which is not S1, so it will depend on the directionality.
Yes.
Yeah.
Yes.
But the question
Because
here is
wait,
these devices, how do you control the directionality? How do you even know that there is one, right?
Nobody knows. That's the first good thing. I can publish few papers just caching that.
Yes.
But on the serious point, indeed.
Because if it was like you said, it was grain boundary. So grain boundary means that the order parameter was coupled to the crystallographic direction, right?
Mm-hmm.
Yeah.
Mm-hmm.
And here,
Always like
it's
that.
a single crystal.
So I can say that GLD basically shown some directional dependence, like nematicity. Like he showed that superconductivity has some directional.
There's nematicity was shown by a few groups. Yuan Cao already had in the early days nematic.
Yeah, this is in twisted.
Yes, twisted.
Yeah.
So you call it directional grain boundary. Grain boundary is that's George. Yeah. So here the challenge is if there is a direction, you need to couple two different directions within a single device, right?
You have different contacts.
No, but
presumably, in
If
general.
the direction is dictated by crystallographic order and your material is rhomboidal graphene, it's a single crystal.
Yeah, so if you have kind of a more elaborate structure with different contacts.
Like many polytypes within the same flake or something, or
Several contacts are not always there.
no? But the contacts don't.
No,
don't
that
have-
inhomogeneity is
contacts don't have-
something different, right? Like if you have ABC and AB, that's a different thing.
No, I mean, just with different lattice terminae.
Well, lattice terminate again. Lattice
I mean, in the
termination.
sense that you could, like there's.
So you're
X,
saying
Y,
if there's a
Y.
lattice, okay, saying what you're saying. So you say if there's a lattice termination, suppose you have your device and this is the top view of the device, and then suppose it's a D wave and it looks like that, okay? And then you say, okay, well, I can want to probe it from this direction, from this direction. Okay, yeah, one can think about that. But how do you do that? It's not sure how to do that.
I mean, this is in a way, as I said, that from the noise they're trying to simulate them. Sorry?
Yeah, well, Shahram's QTM, yeah, that's
Yes,
of course,
QTM is a good idea, but I understand that only. Yeah, the thing is that we need both the gates, and I think in quantum twisting spectroscopy can apply.
Yeah.
Might the
And
gate
that's
from
what I'm
one
saying. You
side.
can. That's the only one that you can think of.
He can if you're like two rhomboids or something.
No, but don't need the QTM. You can have also devices with few angles.
But this is the thing, Yuval. You don't know device to device. What I see by eye is not,
No, but the point is interesting here because suppose like a tri-layer graphene, which is not a crazy device to make. Because suppose you have ABC to ABC and you twist it, which I'm sure Shahar probably talked to you about it 10 times because it's a good idea and you already thought of it. It's a good idea. He's probably already showed it. So the point is that you actually have only one gate to the top and one gate to the bottom. You actually don't have degree of freedom of two individual gates, right? But still, you can probably with the two gates control.
But the QTM just allow you to do things continuously. But you can also have device with few angle.
No, but this angle, how do you define? What is this angle? That's
It's
what I'm
the
trying
angle
to say.
between the crystallograph
measure.
This is what I'm saying. When I'm
Yeah,
looking
that's
at the
something you
plate,
can measure, right?
No, but
It doesn't, you don't need to know what the angle is, you need to know that you're changing it. That's the point. You don't have to know absolutely where you
oh,
are.
this I know, but I'm saying that then it's again a bet, right? I hope that I'm changing. But if it's a different device, how do you know that randomness, right?
no,
It's the single.
what do you mean?
yeah,
You're because you don't know the crystallograph.
Yeah.
No, but you do. Okay? If suppose you have an ABC flake,
Mhm.
you do tear and stack. Tear and stack. You know the random.
That's what it is.
So you do tear and stack, but instead of putting a small angle, you put a big angle.
You do what? What?
Tear and stack.
There, like
How are these devices
Tear and
built?
stack.
So how does Mikhail build the devices? She tears and she stacks,
I
right?
didn't understand what is tear and stack.
So okay. So
This is the nearest.
are you happy with the
But
result?
if you have these two gates, can you make a short bridge, small region where there is no gate, and then just the QTM there?
Basically, what happens in this situation is you have suppose you have let's say suppose you have a graphene here. Suppose this is an ABC graphene. Suppose this is an A graphene. It can and there has to be a tunnel barrier between them. And let's say it's some kind of a TMD, which is supposed to be
Why
TMD and TMD. Transition into lithium carbonate.
No, but why
You need a tunnel barrier.
for what?
Because I was assuming.
No, I want. So you just make a usual one-way graphite.
Yeah.
And then sort of you need the HBM and the graphite gates, but can you kind of just cut the region where you don't have that, and then do your sort of QTM there, and then let's say hope that superconductivity
But
device.
you need to be able to tune. If you want to measure superconductor, you want to have two ABCs.
No.
You need to tune both of them into
In this case, you would just do tunneling to the superconductor as a function of the angle, because QTM is like ARPES in this case, but just a low energy ARPES. So it gives
Not
you.
necessarily. It measures transport depending on angle. So it doesn't necessarily. You need. Okay, there's a point here because you need the two graphene K points to align. If you apply 45 degrees, you're not going to align.
Yeah,
So you're not going to have momentum
that's
conserving.
kind of the ARPES.
You'll have tunneling, but not momentum conserving. So it strongly suppresses the tunneling. That's true. So maybe QTM here is out. Okay, that's a point. May not necessarily want to have maybe graphene. We could have something else coupled with graphene, which is not. Because the big thing about this whole technique is that the K point of graphene is very strongly defined. So he scans the K point against each other.
Yeah.
K points against each other. Okay, so Mitali, so we talked about all the parameters. What are you were also talking about chirality, right? And about magnetism. There are like 100 questions there. So maybe until you have 20 more minutes that we have to run. So
If
what
people
else
are
you wanna
enjoying the questions, we are enjoying the answers. I have half an hour. I can spend even the rest of the day if I don't have to get the train.
Yeah, but you're running a panel, so you want
to stop?
No, I wanna ask you other. You had 5 questions. We're only talking about 1.
Oh, so we go to the next one.
Yeah.
Oh, sorry.
That's what my
Why?
wife
There
was saying.
are other stuff people want to take over.
The plan was that you're running the first half and the rest after you leave us. We do the others in the second half. So you said
So the parent state of the superconductivity is also kind of not
it's
so.
just let's switch this on.
And also, what is this mechanism for this field strength, like field induced superconductivity?
I can comment on that.
Yes.
There are few theories going around. I don't know if they are correct or not, but one of them explained that was developed by Gal Shavit, was saying that as you apply a magnetic field, you shift the spin Van Hoff singularity. So if you have large density of state for both spin up and spin down, then you have the Stoner instability. When you apply magnetic field, you separate them. So now one of the spins can have higher density of state and give the option for superconductivity.
Again, you have if you have the
So you spin up and spin out down on the generator.
you start with the stoner
So there
instability.
is a Stoner instability. Now imagine that you apply magnetic field. So now it's spin down, it's more occupied than spin up, and you can approach it kind of suppress the Stoner instability. So you can approach the high density profile of spin down, and this open up the.
But if it's next to a quarter metal, that is basically you have lifted all the literacy, only one spin you can
No. So it's you take advantage of the high density of one spin and the tail of the other. So you just somehow suppress the Stoner instability, and that also happens in this experiment of Nudge-Berger that push the system to have spin orbit coupling.
So he has because he uses a substrate which is
He had I now forgot the material, but there was a TMD with spin orbit coupling.
yes.
Then when you push the electron wave function to the TMD, suddenly there is superconductivity. So the idea was that it's the same kind of mechanism.
Sorry, who was?
Stefan Berger, that's the experiment.
This is Caltech.
It's a bit problematic to pronounce his name because he's Serbian and he has Hungarian name, so I don't know now there are actually too many people in the world who really pronounce it.
So kind of to explain both the Nudge-Berger experiment, is that sufficiently close?
I don't know how to pronounce Hungarian.
No, it's not sparse. Nudge. It's
Sufficiently
NADG.
close or
Not sparse.
different? And also when you apply magnetic field, so it's kind of the same mechanism that.
So the spin orbit.
Spin orbit also separate spin up. It's a I think spin orbit, so it also separates spin up and spin down.
I want to make a proposal for the schedule since we have until 5 and the 4 of us. So maybe we switch to another set of questions now to one of you. Maybe if we're already in the realm of high fields, so we switch to your questions.
Yeah,
maybe?
it's maybe related to you.
So yes, we were looking at it should be. Let me look for it. It's also PDF, right?
Yeah, it's so questions.
So if you really see what I'm asking. I don't have.
I can.
This is
This one is, I think it's called.
final one. It's yours, isn't it?
Yeah.
Right?
Yeah, I guess the question is, well,
You have 5 slides here, so you will.
no, it's
you
just to
wanna
show
manage
that,
the-
I don't know, it's just a kind of, okay, no, it's, the only thing is, it's less of a fundamental question, it's more of an, whether this thing was observed or not, and kind of thing, that's an open question, so the idea was.
So maybe you stand up and I'll be the guy running the slides, okay? So, okay.
No,
I'll be
it's,
the
I mean,
slide,
there's,
slide,
yeah.
the slide replacement, switching. You explain.
Yeah, no, so these are just different experiments that somehow.
So we
have
switched
some
from
relation.
carbon to TMD. We're in NBSC or
Well,
TSC
I
now.
also have carbon here to say. It's just kind of I don't know, circumstantial evidence, I would say, of potentially nodal spore web. So this is this
What is
symmetry.
this over there?
So this is the critical field as a function of directionality. There's some 6-fold symmetry. This is in niobium diselenite.
That's the group of Lords.
It is
Not too many groups.
We discussed this.
Lords.
Yeah.
I actually asked him to come and have answered them. He would have been here if he answered his email. It would be nice to have him.
Everyone is fun.
Yeah.
So this is, let's say, one, then maybe if you move to the next one. So I guess
So that's the next
would
slide.
be
Okay, yeah. This is
Heinz results. Again, different material, but again,
but that's not parallel field. That's just STM on it.
correct. No, of course, yeah. But again, kind of potentially some indication of a nodal. The fact that there is an edge, like states on a stepped edge. So again, some potential indication of a nodal superconductivity. Then the next one is the V-shaped gap, which again is.
This is TAS2
exclusive, of course.
grown on something. That's a very weird result in TAS2.
This is no magnetic field, isn't it?
Yeah.
That's the only.
That's a group of linear.
And then what is the last one? Ah, yeah. So this is the
That's probably right.
left beam.
That's
V
the-
shape,
That's the experiment that we're doing, the tri-layer to tri-layer, right?
right? So this is again V shape, and also there's additional indication. Let's say the dependence or how the gap is destroyed with magnetic field and temperature. How does zero bias dip is destroyed with. So I think that's so.
Okay, yeah, so now the experiment, so what you're saying is,
So the question is, I don't know, do like are any of these? And there was also yes, the data which I didn't get, but from the Tristan was showing on flakes where it was showing some kind of edge states in certain directions and not in others. I think.
it was showing STM yesterday, showing STM on misfit samples, where it tunes the from lead to lithium on lead to, and the intercurrent rocks. They actually tunes the population of the DMD levels.
And then there was one of these plots. So I'm sorry I don't have it here, but one of these plots seemed to show like
Right.
conducting state on some surfaces and others. That seems to be rather no. And just this is like a couple of suggestions that people had in the literature of how to detect. Of course, V shape is not unique. Or many of these things are not necessarily unique.
How do we know if we have a nodal superconductor? So before Elke said V shape is not enough, right?
Yeah, V shape is
V shape is not enough. So what else do we need to know?
What is edge states? Do they only so this STM, let's say the tensor states? Do they only appear in the state also?
Nodal is nodal. It's a superconducting state. It's a superconducting ground state.
No.
Oh, in
In
those-
experiment.
in this is so I
Because as you showed, if you have a let's say honeycomb structure, zigzag edges have
right.
edge states
But
in the normal
this,
state.
The normal state, right?
Yeah. So
Actually, the scale doesn't make sense at all here, right? Delta is huge.
Here, this measurement? No, this is not delta. I think the delta this is
It gets out to 0.1 or
I think their gap is about 0.1, about 200 to 200 microfarads.
that's 1 Kelvin.
that's 1 Kelvin. That's reasonable. No, but I thought the other was much bigger.
I actually don't know. I don't remember at the top of the head what kind of delta people measure. But I think that the experimental
The whole thing
observation
is non-conventional superconductor, so the ratio between delta and T, not what you expect. Not part 2, part of 10. And,
No, but-
and the walls that are around, it is not the superconducting. It's some
the V shape is not the superconductor.
this for this one for the.
okay,
Which way does the ratio go? Is it
much big. Delta is much bigger. And
ah,
people believe that this is related to the bend structure, some reconstruction of the bend due to interaction, which is non-trivial. And indeed, there are experiments when there is a gap at low energy disappear, and still there is a deep, but maybe not historically.
This heavy fermion.
Maybe one of the explanations.
another one would be Hana resonance Bondo, yet another one is just a renormalization of the conductance due to the lowness. There are many reasons that give rise to V-shaped
Right.
reaction.
Yeah.
So, but you say stuff that gives rise to V-shaped spectrum, which is not even a superconductor. Miguel, you wanted to say, do you have a comment?
Yeah, I want to make a comment on the, there are many STM, STS papers
Yeah.
claiming nodal superconductivity based on the shape of the V shape of the superconducting gap. But my feeling, I'm going to say something that is not politically correct. But my feeling is that the literature is full of papers claiming this, that nobody takes care of the electronic resolution of the system.
Yes.
Especially if you're dealing with gaps that are like 0.2, 0.3 milli-electron volts. You have to be super careful because radio frequency goes into your cryostat and broadens a lot. And then probably closes the gap. You see a beautiful V-shaped gap that you claim it's nodal, And the problem is just that even if you are at 100 millikelvin, effectively you are working at 1 Kelvin. And
like this,
unless
filters.
someone shows you
Filters.
the,
You missed the whole day that people were talking about filters.
okay.
All the SAT
Now we
questions
feel.
were about filters. No, but you could say the thing is that basically what you're saying is that if you can take a good old PCS, maybe without strong quasi-particle peaks, you smear it with the Dines parameters, you get something that looks like a V.
Yeah, exactly. So the way to go, at least, is, well, if you think it's a novel superconductor, and if you see this V shape, at least show a reference experiment showing the limited resolution of your setup.
So that's why you showed your aluminum, right? You showed
That's why we go for aluminum.
That when it's a same gap but with a U shape, it's a
Yeah.
Now I understand. Now we understand why you showed the aluminum.
Yeah, but still I have questions about the aluminum, but we can discuss later.
Yeah,
One
okay.
other time.
Yes.
Yeah, I think you're totally right. So there are many claims in the literature where people show a dip and say this is unconventional superconductivity without any control, and here no coherence peaks. So I think this is just showing one curve is not enough. We need to show temperature dependence, field dependence, control experiments, all these things.
But my question is, suppose you do the control, you get like what you did with the aluminum. You can do the for HB on the H, you get the U shape, on the V, you get the V shape. You say, okay, yeah, I have very different curves. Okay, so if you get a V shape, it can still not be. You still don't know, not sure it's a node, right? So what is the? So people do thermal capacity. Heat capacity you can measure directly in bulk materials. You can measure because then you can measure there's a particular relation for a S shape for fully gapped and not for fully gapped. That's something that's been known for a very long time. But in a very small scale devices, you cannot do that. And for example, in a 4HB, if you have a chunk like the T layer is V and the HS, you can't do heat capacity for the whole material because you get the average, right? So because if it's about material, you can do heat capacity. Heat capacity is known as right?
Probably another also indirect way would be, well, usually when you have a P wave symmetry, then you also would have triplets and trying to show something that is only working with triplets, so some spin dependent things, long range transport in a ferromagnetic system. I think a combination of measurements is necessary.
But that's assuming it's a P.
It's assuming it's a P, yes. A D, well, and I showed it briefly, I think so. You can distinguish in principle between P and D just by the shape that it has in the gap. So you then really need to make a detailed comparison whether it's better to a linear or a quadratic shape.
Yeah.
Then you could guess whether it's P, and if you spend usually the V shape goes with P, or is closer, let's say linear V shape really is closer to P wave, and then you would expect to have lots of triplets. And the triplets you should see in some magnetic behavior. But it's all indirect.
There's a point here which, Ganit, if we refer to you're talking about this, in several situations the node only appears at high magnetic fields. And that makes life harder. Yeah, because you need to measure the very strong parallel field, and then it also gets to smear your signature.
But I'd say at least something that is, that has this kind of lattice directionality dependence is really kind of an indicator. So either versus something different spaces, but also just
yeah. Something just you were showing V shape, H state, what's the story? So current space relation.
Yeah, no, just to say again, so some kind of spatial or termination dependent. If it's a nodal phase, that would be really fair to say it's more done, but that would be very proof something that is really dependent on the lattice termination. So either current phase relation with a different terminating phase, for example, but also just
So it's once again the grain
different,
boundary
bound-
experiment.
Yes, exactly. Different boundaries to the next phase. No. What matters is the lattice termination. So different junctions. Yeah.
For this, you need to be in a clean limit.
Yes. For these, yeah.
I had a stupid question. So why wouldn't night shift be doable?
Night shift? Because you have to explain this to us. There's some people here who don't think that night shift is something you do when you're in the hospital and you're a doctor. It's not the end with the K. Yeah, so not everybody knows that it starts with the K. Yeah, so
what is that?
NMR.
It's an NMR feature, but that's all I know how to say, yeah.
Yeah, I don't know much more. I know it can distinguish between the S and P wave, for instance, and for organic superconductors that have been.
It's also about property.
No, an
I'm
NMR
sorry?
is well, true.
It's also about you need quite some material, I think, to have a sufficient signal, and then it's usually also only very subtle differences in the shape of the dependency on what was it, temperature or so, when you go underneath the transition temperature. I remember the story with the strontium gluconate that for a long time has been supposedly a triplet superconductor, and this was some slightly different interpretation of the data also in night shift experiments, and this it depends on these coherence factors, right? So it's a subtle thing. I think it can give input, but it's also not a smoking gun.
But what does it actually look for magnetization? What is the night shift?
So maybe
Go ahead. I'm not a specialist at all.
I'm not a specialist, but because of the triplet stuff, I did some reading. So the night shift, I mean, what I understand from the helium experiments, maybe somebody knows better, is that basically you're doing NMR, so it's a resonance experiment, and then everything will resonate at G equals 2, basically. Like even the random spins in your sample are gonna recess at G equals 2. So definitely you see some peak. And then what allowed them to identify the helium-3 superfluid phase was that there were actually, so you have these pairs, and then you have actually dipole-dipole interactions between the pairs, and that shifted you away from G equals 2, and that's how they were able to identify the superfluid phase. I mean, if there is something similar in these systems, which I'm not sure if there is, but again, I don't know. Maybe you have some idea in mind. I think this could be quite interesting, because now, as we all know, people are able to detect single spins, right? So Patrice and friends who are just CA not far from here, they're now able to detect single spins with lumped elements circuits, essentially. So then we get rid of the need for the bulk. But then for me, the real question is what is going to precess at G not equals 2? You need some shift away from the usual resonance. Otherwise,
it's a lot more frequency, right?
Yeah.
They're detecting something with a frequency.
So if you don't have something that shifts it away from 2, then you're just going to pick up every random spin that lives in your environment.
If it's a singlet superconductivity, then you lose the spin, you lose the signal.
Okay,
I think
so
this is what they made. How you know that it's an S wave, and if
okay,
things
so
like the top disappear.
you're saying that you look at
I
G
think-
equals 2, and then you do something that turns off the triplet, and you drop the amplitude.
Yeah,
Okay, maybe
singlet-
this is
I think
possible.
this is how they identify singlet superconductivity. Like it just goes
Yeah.
when it becomes superconductor.
Okay.
If it's something else, then
Yeah. Okay. That's right.
but
Just some Miguel and then Taro?
So I don't think there is a magic smoking gun technique that's going to give you the right answer. But so if you look back in time, 20 years ago, the ITC people used to study the QPI interference of non-magnetic impurities in D-wave superconductors in order to prove this D-wave symmetry, which is novel, right? And because non-magnetic impurities are pair-breaking if they are connecting sides of the Fermi surface which are opposite in sign.
Non-magnetic
Non-magnetic impurities. If they are connecting sides of the Fermi surface that are opposite the sign, then you can see something in the QPI in STM. So maybe that would be one way to go in these new systems that we are QPI exploring.
But if you look at the material, like the system that you've been looking at, is it to disorder to see QPI or something? I guess you probably did it. Like in the surface of 4HB. Surface of an T site 4HB.
Well, you can deposit an atom.
Because you need to deposit the atoms.
Well, you can try to embed in the, for example, replace an niobium atom by molybdenum, as we did in the past. But another approach would be to sparkling them.
Yes.
In the surface as atom.
Okay, and then you have a selection of directions because each orientation. Okay, I didn't know. Taro, you wanted to make a
Yeah, so to my understanding, one of the questions in this PMDs all is the kind of valley dependent gap. So you can have an F waves conductor where the gap is changes sign between the valleys. That's a triplet state. And then the QPI.
It's spin triplet or orbital triplet?
Sorry,
it's a true
spin
triplet.
Yeah.
So what was the situation again?
Let's say valley mod delta, which would be then also a spin triplet. So and then the QPI would have to depend on whether you put the impurity. But you sort of what is let's say you put an impurity in a atom of the honeycomb, and then you study how the QPI depends on A versus B. Here. Then there's another way, because then it's a triplet state. So triplet state creates a time versus symmetry, and in principle, at least, time versus symmetry can be seen in kind of optical spectroscopy, like in MOLC, magnet-optical current effect. The corresponding analog in this case would be microwave spectroscopy, where you would see like transverse signals also. But that would require a kind of complicated microwave.
Well, I think I have a feeling that following what was presented in the first few days, there's a lot of progress in embedding superconducting sample inside circuit QED.
Yeah, but then
it gives you a lot of
kind of
resonant techniques that you were talking about, like NMR. You can actually do much more local things, like
MOLC describes chains of polarization. So let's say you send S polarized light, and then you see a P polarized signal in response. So you need to have a correspondence of S and P polarization in your microwave setup, which is not so
easy. Okay. So we start. Do we have any other comments on the V shape? Or Ganit, is there any other thing in the V shape manifold that you want to discuss? Or we move to the next set of questions. So Karis, we are moving the discussion to your questions, and this is this PowerPoint. This one, like surface.
I didn't do a PFM.
But you patient. Yeah, already here it is.
Yes. So before there's any comments, I would just like to say that I found out yesterday that I'm on this panel. So my questions are very down based on
you can turn it to your side.
some problems that we are having at the moment, which hear a lot of
when you talk to them, face them because they can't hear you.
Okay. Everyone can hear me when I'm seated, right? Yes.
When you speak loud, yes.
Yes. I have to turn on the lecture theater voice. The voice you use when you're having lectures. So I think many people in the community have noticed something, which is that when you talk about TCs of van der Waals superconductors, there is actually not even a consensus on what is actually the TC. So here I'm showing two different experiments. I don't think the fact that they're 10 years apart is very relevant. But if you look at the devices, they're very, very similar. Each of them is encapsulated with HBN. Okay, the guys on the left said somehow the monolayer didn't work or something. I'm not sure what happened. But if you just look at the TCs of these guys, okay, the bulk is pretty similar. So everybody agrees that the bulk is roughly here.
7. Their bulk is a bit slower than what's 7.
Yeah,
maybe SC2 is with 6, 7, yeah.
close enough. But take a look at the 2 layer. So it's like right above 5. Then forward.
Right about 5.
It's a bit more to the right, I would say.
5.3, yeah.
Okay, but then look at 3 and 4. I mean, you can already see without looking at the numbers that they're going to be different because 3 and 4 are stuck together here, and 3 and 4 are fully spaced to here, right? And then if you look at the numbers, 3 and 4 are 5.5, and then 3 and 4 are not 5.5. 5.5 is here. So okay, so basically you're doing transport experiments. Maybe you guys have other things in mind. This is what I could find that was stuck in my mind. So even in transport with very, very similar devices, people are not finding the same TCs. And then you do tunneling stuff like what we're doing with Panar and also a couple of other groups, then things get a lot worse. So so on top is tunneling data. So there's this stuff from Castanova. So it's from
This one.
yes, on the left. So it's from the group of Gaim and Manchester. And this is probably the most similar to the transport guys because they have encapsulated totally in HBN on both sides. Yes.
Okay, so I think the work by Xi, which is a King5 math work,
Yeah.
they put it after keeping the sample outside for after 1 hour. So they expose it to air for 1 hour, for less than 1 hour.
Mm.
Then they put the boron nitride. So basically, I think it's useless. Whereas the Manchester people never exposed the surface to air. And it took them like 10 years.
Numbers.
Huh?
You get lower TCs.
I don't care. I don't care, but that's a big difference when you go to
Do
the
you know about
reality
these guys? What are they doing?
For that one, I have no idea.
Okay. Yeah, so in Manchester, I mean, you can see very clearly and directly. Okay, so Miguel is saying this is the good one. Okay, good. So we look that, wait, is this the correct one? I can't, maybe I took the wrong picture. I'm not sure. But TC as a function of, TC as function of layer number is not aligning to what we're seeing here. I think this may not be the right picture because
It looks like transport, right?
Looks like transport, not like tunnel.
no. Yeah, I think I took the wrong picture, so I have to look for it. But I'm sorry about that. But they got very much lower numbers. This is some of our stuff, and you can see the numbers are even lower because this is 6 layer, and this is 2 layer. It's the 2 things that we showed you. Okay, now I'm sure this is not the right figure because the next thing says that for Castanova, unfortunately, and despite many attempts, they could never get tunneling spectra for monolayer MBSE2. So I'm sorry about this. The figures are all lower. And then for us, also, we've never been able to measure the monolayer. We made several devices. And the lowest TC that we ever saw in Orsay is around 1.5K. I didn't have time to check last night if it's 1.2 or 1.8, but it's there. And it was about 3 monolayer, which is crazy. Okay. So
This is aluminum.
yes, so this has aluminium as electrodes. Then, so all of these leads me to think that whatever is touching the surface is probably important. And of course, the more fancy stuff, this is stuff that we worry about. And of course, the more fancy stuff you have already seen, by putting the right thing on top, you can get superconductivity. And in Twisted WSE2, these are 2 different papers from 2 different groups that see superconductivity at not exactly the same angle. I think these guys are 5 degrees, and that's like 3 or 4. And then recently, superconductivity was seen in Twisted T2. This was already mentioned by Vitali. And also there's plane ferromagnetism in twisted W SE2. So I mean, it's exactly the same system as previously, just a different angle. So all of these leads to, while we're doing this, I'm going to try and find the Castanova correct graph. So the question is, has any pure TMD superconductor ever been measured? This is a question I was curious about. Maybe somebody knows.
Monolayer? Oh, monolayer or
I'm not aware of the system of a
sensor? Monolayer, pure monolayer basically.
Oh, one layer, two layer, few layer. Yeah. And I'm not available. I mean, we have a flip time of a monolayer. It looks like crap. I don't want to show it.
I can tell you that I tried when I was in Colombia. It's somehow we used to use this pre-made contacts.
Yeah.
I don't know if you know that's
the VM.
yeah, that's the thing. I tried 2 flakes.
Yes.
They were not superconductor, and I was doing it inside the glove box, like exfoliating the same day and making the divide, like making the stack that being that 12-hour window or whatever was the myth in Colombia. So,
Yeah. So I don't know, Jericho. We tried like 3 times.
he has commented.
Just so again, then Shamashish.
Yeah. So I think one comment. So I think you guys are basically ignoring epitaxial samples.
Yeah. What are we? We're talking about exfoliate. No, not epitaxial.
We're studying monolayer
I'm talking about yours.
and BSE2 have been grown
Yeah.
for decades, and actually not just for STM experiments, but also for transport experiments. Shui in China has made beautiful transport experiments on these epitaxial layers.
And can you say more, because I'm very ignorant about this.
What? If I can say more?
Yes.
No, it's just not common. Epitaxial layers are in general ignored by transport people, but I don't know why.
Epitaxial layers, you mean grown on an insulating substrate, epitaxially, not freestanding, not transferred, but grown on a substrate. Or what is?
Well, there are several substrates that work. STO, bilayer graphene, graphite. I don't know if BN works as well. Sapphire.
Does the TC depend on the substrate?
Using epitaxial layers.
Yes.
Probably yes. But I mean, I'm just saying that.
I agree that this at least in tunneling that your community does that, and the question here is whether the same trend in TC versus thickness exists there. For example, people measure like the 2 layer, 3 layer, 4 layer.
Yeah, no. The problems with epitaxial layers is that you go to 2, 3, 4 layers, the crystalline quality of the system goes worse and worse and worse.
It's not deteriorating.
So, particularly fully trust the monolayer, the second layer. For example, if you try to look at the channel wave from the tri-layer, in the uppermost layer, you don't see the channel wave. So probably it's not good enough.
So you say that as a data point for a monolayer, the epitaxial is a good reference system.
I don't know.
But if one wants to do like thickness dependence, then you start running into practical problems with the quality of the growth.
Yeah, I don't know. I can give you an example. But 10 years ago, we were measuring a chance wave in niobium diselenide with STM, and we measured. We have access to the real space, and we were able to measure the TC for a chance wave in a monolayer. It was 33 Kelvin, so basically the same what you find in bulk. Yeah. But at the same time, in parallel, some transport people.
How much is it?
The charge is 33 Kelvin, 35, something like that.
Yeah.
But in parallel, a transport group published a paper claiming that in the monolayer regime that goes up to 200 Kelvin. But
the charge density wave.
Yes. But why? They expose the samples to Earth again.
Yeah, but this is
I think that pinpoints the chance to wave. Defects pinpoint the chance to wave, and they admitted that the samples were exposed to Earth.
So what you're actually saying is that once you go to the interesting limit, a lot of the variability between the samples is the pinning of the charge density wave because the density, the sensitivity of the sample to the disorder is so much.
I think that in general is a fact. If you have a pin, the chance to wave pin's there, and I think that increases the chance to wave. I don't know if it's a heavy contamination. I don't know. Luckily, I think my feeling, that's nothing, that's my opinion. I think the superconductivity is less affected.
Okay.
So there are probably variations, but it's less affected. It doesn't really matter if you have a contaminated device, as long as the bulk drives for the chance to wave, it's the worst thing that you can do.
Okay, just Shamashi, she wanted to make a comment.
Yeah, so I had two comments that, I mean, many years ago, like 16, 17 years ago, I struggled for 1 year to contact ultra-thin NBS2 layers and completely failed. This was before boron encapsulation entered the picture. And there are two notorious problems with NBS2 which are known. One is that rapid oxidation of the surface, and second, loss of selenium atoms.
Yeah.
So encapsulation, I can understand, is extremely critical to save the surface. The second comment is about the superconductivity. Is that, I mean, we know that all these materials are heavily, the TC varies a lot with pressure. So with pressure, for example, bulk NBS2 crystals, the TC can shift with pressure. Then it has its cousin materials like niobium triselenide and all, which are not superconducting at ambient pressure, but they become superconducting with some amount of pressure. So in ultra-thin forms, I would guess that the strain or the substrate influences the TC a lot.
Yes.
I mean, so it's no wonder that different groups are seeing different values of TC, because that is exactly what is to be expected. And the third about this charge density wave is, so I do not remember it I think there was a paper on ARPES around 2012, the first author was Borisenko, where they showed the existence of a pseudo gap in the charge density wave state at temperatures way above the charge density wave temperature of 33 Kelvin. So I do not know if it monolayer that is amplified and one sees the charge density of high temperatures. But there was an ARPES paper which found remnants of the CDW way above the TC of CDW in NBS2.
So how do you interpret that?
I have started following this for a long time back and I do not remember this, but I remember that there were reports that even bulk NBS2 has remnants of CDW way above. So maybe
You said remnants of CDW?
Yeah, the charge density, not long range order,
but local. So
yes, exactly.
Yes. The actor was not aware of that.
So I will try to find this paper, but I remember there were some studies around 2012 where these were reported. So I can search for
That's ARPES, not this thing.
maybe both. At least I remember one ARPES paper, but I'll try to look for it. Because there's this whole question of whether NBS2 being a quasi-2D material, the CDW comes from Fermi surface nesting or other materials like quasi-1D materials like NBS3, it's clear, it's nesting. But NBS2 had this long debate if it was nesting or not. And this paper seemed to have settled it at that time, that they found some evidence for nesting behavior. And they also
evidence for nesting, you're saying?
Yes, the Fermi surface nesting. And they claim to have found some signatures, and apparently there were some signatures of CDW even above TC. So, I mean, this is for bulk.
Above TC of the
33 Kelvin.
Above 30 Kelvin.
33 Kelvin.
So just two things. I mean, first is the oxidation. I can believe the selenium is disappearing, but for the oxidation, I'm not. Correct me if I'm wrong, but I don't think FIPTAM has seen any oxygen so far.
We cross-section almost each and every device. Now, at least in the tunneling devices, they are by definition encapsulated. And we do FIPTAM and metal analysis, and we see no evidence for oxygen or selenium deposition at the top surface.
So there is a superstition that NBS2 oxidizes. So it will be more accurate to say it degrades in an unknown way. Because, I mean, as I don't know anyone who has seen oxygen so far in a FIPTAM. And then the second thing I was going to say is the CDW. I don't know if this how this merges with what you know, but I saw a paper very recently that did the MO substitution to MB, and basically at a very small substitution fraction, they killed the CDW. So it seems very sensitive to kind of.
Did it affect the superconductivity?
So what was interesting is that you put MO in, and a very small fraction of MO, the the superconductivity actually gets better. So the TC goes up, and they claim that this is because they killed the CDW, and so the superconductivity.
I can accept this.
Yes, and then after that you have the MO basically killing superconductivity because you're going to MOSE2, which is a semiconductor. So just to correct something I said, this is correct. So they were able to measure transport on the monolayer, no problem. They were never able to get tunneling data. And just since we now know is the correct figure, you can see, I mean, 2-layer here. Since Miguel likes this one, 2-layer here, it's less than 5. 2-layer here, it's about 5. I mean, everything is lower. Even the bulk is lower than.
So just Miguel, what you're actually claiming is that because their material was exposed, so supposedly this is like you don't have charge density wave, or what is it
that was the same group actually. It's a group of Kip and Mac, and they published this paper on superconductivity, and in parallel the paper on chance to wave. So
Actually,
I think the differences with respect to the Manchester people, the critical temperature are relatively similar, right? So I think a bit smaller, but I don't know.
So you're comparing these guys to these guys?
Yes, right? 1 Kelvin left.
So this is confined, not that is
yeah, Manchester. I know. So, but on the upper, so the Manchester experiment, they encapsulate. They were the first ones who were able to isolate one monolayer graphene isomer, and they took them 10 years until they published that paper, because probably they were not sure about oxidation or corruption of the monolayers. And after 10 years, they were able to encapsulate it up and down and produce this data. At the same time, in parallel, that paper was published using, showing a slightly larger critical temperature, etc. Which I don't think it's critical, but I would trust more the Manchester people. But chance to wave is way more sensitive to contamination, and that increased up to 200.
Because the year is wrong. It was 2018 or something.
Yeah, it's probably.
So then, coming back to the positive aspects of this, so to my knowledge, and maybe I'm wrong, nobody understands, but this is what Vitaly said, nobody understands why these things are superconducting or ferromagnetic. So I think there's 2 questions. One is, can we actually isolate some kind of pure Van der Waals superconductor? What have we been measuring so far? and secondly, so is everything that we have been measuring just interface effects? This is the negative part of my question. And then the positive part of my question is, if we accept that the interface is going to exist, then what can we do with this? Very broad and open question. And this is a nice review on Bristol materials.
Because yes,
now, how robust is this interpretation of the experimental signature of ferromagnetism? Because there are this whole story of ferromagnetism and superconductivity in LOSTO, and there are quite a few papers also around 2010 to 2012 where he stresses in the critical field data was seen, and it was believed that some groups were having ferromagnetism and superconductivity together, but then these are not reproducible probably, and probably these are impurities. So how robust is this interpretation that of calling it ferromagnetism?
I'm not an expert in this, but at least what I understand is that they measure RXY, and they see an quantum anomalous source.
We're talking about the same paper.
Well, I'm talking about 20 different papers. There were papers by Andrea Young, and there were papers by other people on twisted systems, and in the Rombo-Hedro, people measure quantum anomalous hole. Quantum anomalous hole has to be related to ferromagnetism somehow. Yeah, but that's as far as I understand. And
I'm not an expert in magnetism, so I don't want to comment.
I come from a very.
What I mean, yeah, I mean the reason I asked is that this kind of two competing effects, these periodically appear in many class of systems, and after some years it goes away. So there was this thing phase in LOST also. So I'm just trying to be the devil's advocate and saying that if all these previous stories have been cross-checked for false signatures, and it's a more robust interpretation nowadays. Because LOST was hugely studied and then it completely dissipated away. This.
I want to.
So what did they do wrong? How did they?
I mean, so the thing is, it was not every group were not seeing it, but there are many papers where ferromagnetism and superconductivity are seeing the same samples, and these samples are also cross-checked by other groups, and everybody found the same results. But then one way of fabricating it was not producing the same signatures from a different lab. Like the samples are truly showing it. So the idea was that superconductivity and ferromagnetism were coming from two different parts of the sample. Like they were, it's not a pristine sample which was both ferromagnetic and both superconductive.
Show that, no? That it's the in LAOSTO that you showed that there's some regions of ferromagnetic, some regions of supermagnetic, right? You showed that. The recollection of scanning squid showing something like that.
There was something, but not magnetic and the superconductor at the same time.
Yeah, okay.
But I wanna zoom out to the point which sort of the theme of the discussion that Karis raised is that once you move to the monolayer regime of any material, especially superconductor, you're extremely sensitive to materials which interface it, whether from below or from above. So again, also referring to the comments made by Miguel, if you look at MBE really depends on the substrate, right? Because you grow on a substrate, you really depend on the substrate.
Yeah, that's true. That's why, for example, we measured the critical temperature of naive Dyson at monolayer on 4 different substrates.
Yes.
Barrier graphene, silicon carbide, and we thought, okay, but at the end, this is a metal, so maybe affected. But we grew it on a monolayer boron nitride, and we measured the same critical temperature.
And it's all like around.
If it's a metal,
so it's all like around 3 or something, or.
Yes, something like that.
So I can tell you, if you look at tantalum sulfide, there's a data set from the group in Madrid, from Herman, that he looks at the monolayer, but it's a weakly coupled to a bulk, and he sees one spectrum.
That's a monolayer decoupled
from
the exfoliation.
Yeah, from above. There are several data sets from the group of Lidierot that look completely different, and they look like, some of them look like a V shape, and some of them look like a U shape, and there's a complete zoo of spectra that you see rosen graphite, if I remember.
I think it's graphite.
Bilayer graphene, I think. And there's our data, which is exfoliated on an insulator, which looks
exfoliated, but still you have a metal underneath. No, I think so. I think it's exfoliation, and some of the layers become decoupled, rotate a little bit.
No, when we have a monolayer, it's a monolayer.
But you mean in Herman's experiment?
And Herman, yes, and Herman's gap is a bit bigger than what we see. We are on an insulator, and each spectrum is different.
Can you do suspension?
Depending on if you want to students to stay in your group.
Okay, the answer is no.
I don't know if the students are here.
Hold on, I think suspension is not so difficult. Genting, unfortunately, Mathieu has done some suspended devices with the goal of gating from the bottom. In fact, I think he has one of the papers where he was gating, because there was a criticism of his earlier experiment that is gating from one side, so this is causing some issues. So he actually did a follow-up where he was gating from 2 sides. And the way to gate from 2 sides is that you make a trench and then you flood the trench with his ionic liquid. So it's a pity he's not here. So, I mean, we discussed this extensively a couple of years ago when he was visiting, and it's very doable. I think it's doable. It's not really doable if you want to have a tunnel junction. That's very tough. But the issue with that is that a lot of things that we want to see in magnetic field, so a lot of this interesting physics, right? We want to see it in the magnetic field. Then we the point is you get a really clean MBSE2, and then you measure it in magnetic field, and you say you have clippers or whatever, FFLO, and all this phase, stripe phase, and whatever you want. And the issue with that is a problem with rigidity. I mean, this is something we have to figure out how close of a trench you need to have for the MBSE2 to be flat and not sinking into the trench.
There's a general problem with suspended devices that's been suffered in the graphing community. That because of differences, there's differences in the strain. So sometimes you get these. It looks like a sheet that was this piece of paper Jimmy Lau. You can see the wrinkles, and sometimes it has this hyperbolic structure that it gets a bit narrower in the center. Then it has like a stomach. And sometimes the thermal contraction coefficient of the substrate is not the same as that of your material, and then it either pairs or it just creates these buckling linkages. So it's actually why do people worship HBM? Because it solved this entire the entire field could stop doing suspended graphene. Nobody had to do it anymore, and the people were doing suspended graphene because it was the cleanest graphene. Then HBM came along, and people just stopped doing it for a very, very good reason.
Again, with HBN, I would raise the question of whether there is any moire happening between HBN and whatever is placed on it. I mean, it is a hexagonal material.
No, of course. People discuss this, a line, not a line.
This is important for the structural challenge later.
Second?
That's important for the structural challenge later.
What's that?
For the FCIs. FCIs, you need this more,
But if you don't want anything for a substrate, I think it's very hard to find a substrate that gives you nothing.
Well, HBN, if you look at HBN and TMDs, don't have the same. There's a factor of 30% of the crystallographic period, the period of crystal period. But you have to make sure that they're in the angle that doesn't give you so 3 times 4 more. So if people are still alive, we can switch to the fourth subject of this discussion, which is the other discussion, and that's the following question which I raised before. So that actually kind of harks back to what Miguel was saying about charge density waves. So when I was showing this data on the universality, this data set here, I presented the theory that the culprit for this tunability is a charge density wave. So if you look at a superconductor that's trained, that is tuned in such a way, you have to ask what can be tuned. So one parameter that can be tuned is the coupling lambda. But why should lambda be tuned in this particular way? If you go from thick to thin and thin to thick, it just doesn't make sense that the electron phonon coupling group, maybe it will change, but not so strong. So a second thing that can change is the Fermi, the structure of the Fermi surface, the population of electrons or holes. And again, it's actually pretty well known that if you go with bulk tantalum selenide, they have roughly similar Fermi surfaces. They're not identical. One of the talks before, people showed that they're not identical. They're actually slightly different, but they're not so different. And the TCs are very, very different. 0.8 versus 7.2. So we opted to the one thing that can gap away your superconductor, your density, your Fermi surface is that for superconductivity you need a Fermi surface. And if you start gapping away this Fermi surface in various regions in K-space, you have less and less population which can undergo repair. So we opted for this particular theory. But there are several problems with this theory. One is that people claim quite forcefully that niobium sulfide has no charge density wave. So why is it here to be further up? And if you just do the theory, it just, people don't measure charge density, but in this curve behaves as a bit. Another problem that we have is tantalum selenide. Tantalum selenide, you know, there's very few data on tantalum selenide. Why would you have? How can you explain superconductivity degrading so strongly? You know, people show someone tell you showed before. People will use tantalum selenide as contact because it's supposed to be a metal. But some, you know, you have this ancient paper showing that it's actually a superconductor, but with a very low Hc and very small Hc2. And so it's tantalum sulfide really, selenide really behaves. It gives you such a wide range of superconductivity. Can charge density weight really be the tunes the gaps away the surface, the Fermi surface so effective. What I'm sort of asking kind of the crowd here is, can people think of mechanism that has such a wide tunability of superconductivity? What can tune superconductivity so effective? Basically switching. That's sort of the question we were asking ourselves, and in a way, the community. So, yeah, Tara, you're saying something?
The question is easy whether it has any relevance. The answer has any relevance. I mean, if you ask what can tune superconductivity, what is, of course, then I mean, if you have a conformal superconductivity, you still need to take into account the Coulomb.
Yes.
And if you change the screening of the Coulomb interaction, yes, they still change the DC. So yes, that might change.
Okay, so screening of Coulomb interactions, it's interesting. It would depend in a way on carrier density, I guess. Now.
Yeah.
So, okay, first of all, if you go from thick to thin, the screening would change.
Also the environment.
But the environment, okay, but here you have
carrier mobility also, but if it's metallic, carriers cannot move them.
Yeah, no, but say
Dance has this new star. Also, right? To new star and goes to the exponent.
So how does what exactly affect mu star in the BCS theory? That's something really basic.
Is the parameter, but basically, sort of, it comes from this Anderson or zero potential, and this depends on the exact stretch dependence on the interactions, and it's usually done for the 3D theory, but in 2D case, you have a sort of scientific screening, and in these systems you have gates, which also.
No, this is no gate. This is a tunnel junction, and actually many of these data sets are the thing is these data are measured. Some of them are transport experiments, some of them are tunnel experiments, some of them are not even there. This data was not even measured neither by transport nor by tunnel. It was measured by some kind of electromagnetic inductive response, because the Hc2 was so small. So this data is agnostic of the way it was measured. That was some kind of
what is known about the Fermi-Labo and these things? Are they progressing in a way that we expect?
So that's actually a point that someone told me during this afternoon. Is Julie? Maybe you asked me that. I actually think that except for bulk and certain monolayer, not much is known. First of all, no one that people can do ARPAS on a bulk, people can do ARPAS on a monolayer, but it's very hard to do ARPAS on something in between. And people do DFT or initial calculations on usually. Okay. My guess, I don't know the answer, but my guess is that people have done up initial, and that's something that I should write down in my.
So
in terms of the density.
And my question is, are you just losing density of states? That's why, is that why?
So it's actually hard to say that. You have to lose a lot of negative states to kind of move around. Basically, you have to have like a very continuous gate.
While you put it into an exponent.
What is it?
Really, BCS, you put it into an exponent. So.
Yes, you're right. But then it's kind of weird that it works kind of one way in Ryogan and then the other way. It's true. I actually didn't check the story, so I don't have the number.
Okay, I have a question. Isn't it that in some of these materials you have several surfaces, some of them more 2D, some of them more 3D? Wouldn't you kind of expect that the
Okay, so that's a point that yeah, where we also discussed various forums here during the afternoon. Niobium selenide in the bulk has transition metal D, transition metal, like it was in Lena's talk and in your talk, that you have the gamma and K states of the transition metal. The bulk niobium selenide has the chalcogen P. And this disappears somewhere along the way to the thin. It disappears. It gets kind of squeezed out. Tantalum does not have a chalcogen pocket. It's sort of way below from the energy. It doesn't get folded. So all of that stuff that we see here is irrespective of whether there is or there isn't a chalcogen pocket. So it's all probably dominated by the transition metal.
So don't you see exactly the opposite behavior? It's tantalum versus niobium here. Or am I wrong?
You see the opposite behavior. You go from bulk to C.
Yeah, you go from bulk.
But for the chalcogen pocket to play any role, you would get tantalum completely unchanged because the tantalums do not have the chalcogen pocket.
What about the phonons? I mean, you're also changing lattice constants and.
Good point. So I wonder how does one measure that? So in terms of how the phonons, so Karis was talking about the phonons. I guess there's a way like to measure.
I've initial people can probably calculate this.
Sort of, I've been interested. It sounds like a bit of Deus ex machina. They can just do anything and basically solve this problem. Anybody know a good ab initio person? Or a good psychiatrist? Anyway, I think it's 1:30. I think that's people are probably happy. So Claire, we are meeting at yeah. So
may I have a last question? I forgot to ask it just now about the nodal stuff. So I mean, what we're seeing in Majoranas and things like that are people are sick and tired of transport, which is not giving what they want. So they're moving towards newer ways of detecting these things. Yeah. And so there, well, as I think people know, there are shock noise predictions and measurements from Frey, who is sitting to the left. And then more recently, Olivia Dimitruk, who is somewhere, I don't know which direction in Polytechnique, was doing some theory about how you can detect these things in if you couple the system to a microwave cavity and things like that. Is there anything like this that we can, in the field of nodal superconducting, can you distinguish this kind of thing by shock noise or by some kind of fancy measurement technique that we haven't thought of yet?
So shock noise, yeah. So I mean, the presence of nodal. So the mere fact that you have the nodal points means that you have also, that's also related a little bit to the V shape, although it's not the only way of getting it. It means that you have normal excitations, yes. And so shock noise
could be a way
to
distinguish.
Again, but
is there? I wonder. It's just if there's still probably no one around here knows the answer, but if there's theory, because at least what during the discussion in Stein's talk and Freak's comments, it was assumed that it's pretty obvious how shot noise works as a way to distinguish the order. I'm not sure I know the answer. I know shot noise measures the size of your carrier. So it goes and I know that there are people like Milan Allen who actually look at vortices or stuff and measure the shot noise, or look at selenide and measure the shot noise. But I actually don't know how to read this. Probably well established theory.
Look at the quantum factor and whether it's one or the.
yeah, I'm just referring to the fact
that you have pairs.
Yeah.
Okay. Because if you're looking at the quasi-particle, it turns from 2 to 1 when you go to look at the quasi-particle. If you're so I see. Basically, if you're fan of
Not to be in the tunneling machine.
at low bias, it's a good indication for a nodal.
Yes.
is not.
Yeah, but any other reason to kind of have a subgap density of states could also give you kind of one conductor.
It's almost like the V shape in the sense.
Yeah.
Well, because V shape says there is subgap density of states, but the question is whether the subgap density of states is a condensator. Well, it's
whether it's
Gonna say the fact is sort of, I mean that's the density of state is a quadruplet density of state.
Yes.
That would give you the final factor one.
one all the way.
Yeah, but then if you go towards the unreal regime,
Yeah.
then the final factors would become go towards two. But kind of if you go all the way to unreal, then it's not a bound engine anymore. Then it's again a bit different.
I think a bit more subtle than that. I'm trying to find Frick's recent paper about Andrea processes. But anyway, I can't summarize it like that. We can talk later.
No, but I think, Karis, if we can maybe summarize this discussion, the second point that you raised, you say basically move away from transport and tunneling, and move into something which is more sophisticated, sort of qubit integrated device, like a circuit QED integrated device. And here, actually, honestly, I believe there is a good direction, because there you actually can capacity couple to your device, not galvanically coupled, so you don't have to touch the material. So you can do like full encapsulation with nothing touching your material. Then it's as close as you can get to a model. And then if you can study a galvanically coupled part of the circuit, and of course you can check its TC. Checking TC is a bit issue because they try to right? You should be able to check its gap. Right? So something that I think is worth thinking about.
Well, we need some theory before.
but for I don't know if
It's always in theory.
I don't know if you were referring to Majorana necessarily or just
No, I'm not talking about Majorana at all. I'm saying here's a superconductor. I can't touch it. It's very well protected. You know, it's like in a mausoleum that they keep the body of the leader in a glass cast. You can't go near it, but it's there, and you should be able to measure it and see it. So it's something that you encapsulate super well, and you can look at a small grain of the material, which is maybe a square micron. And then, yes, you can couple it to the outside. Now, what are you going to do? And in my opinion, there's certain things that you can measure it. You can look at the response to RF or to microwave, and that's going to tell you at least the gap.
Mark really talked about.
What is that?
Mark really talked about this during the discussion. What quantum capacitance?
Quantum capacitance.
Yeah.
So who talked about?
Mark really.
Because Marco is not anymore here.
No, so that's something that.
But that requires that the carrying density is very low.
Yeah, no, you can't.
In that.
Quantum capacitance is more of a property like graphene stuff or something, but you can measure.
No, it's basically it's a compressibility of the electron gas, and then you can see what happens at peak. And but typically, it's like a field effect in a superconductor. It's a very tiny thing in a usual superconductor. But in a superconductor with a low carrier density, it can show something.
Yeah, but if you want to look at something which is like these materials, that their carrying density is pretty high.
Then
10 to the 15, it's 10 to the 15 per centimeter on a monolayers. But yeah, but still, I think there are things to do once you go to this direction. Okay, good. Thank you very much, everybody. So.